In today's lesson, we're going to be introduced to a new concept, the concept of slope. And particularly, we're going to look at it in terms of it being related to the rate of change of a particular situation. So I want you to take a minute and I want you to think about what comes to mind when you hear the word slope, just in your everyday life. So I'm going to talk about a few things that come to my mind when I think about the term slope. I think about a hill, I think about a steep hill, some kind of an incline of some description. I might also think about, signs that I see on the road, like this one right here, where there's a picture of a truck going down a steep decline, right? So a sloping hill. If you've ever done any kind of construction, you might be thinking about the slope of a roof line, right? So for instance, sometimes you might be asked to build a roof with a steep slope, and other times maybe the building requires a really shallow slope, right? But those are important differences to know about, and knowing how to calculate those differences is really important. I'm not sure if you're aware, but in terms of accessibility, people with disabilities, particularly in wheelchairs, need to have ramps that are built to a certain standard. So for instance, a gentle grade ramp would be most likely the requirement, because with a gentle grade or a gentle slope, a person will be able to wheel themselves up that ramp, as opposed to a very steep ramp, right, where there's a steep slope. If it's too steep, then the person in the wheelchair will have a lot of difficulty making it up that ramp against gravity. It requires a whole lot more effort. Some of you might also have thought about roller coaster rides, right? So if you're a thrill seeker and you enjoy roller coasters, then the degree of the slope of the roller coaster will be really important. So here there's a pretty extreme sloping decline, and that's what makes the roller coaster interesting to ride, right? So really, when we're talking about the slope of a line, we're really just talking about its steepness overall. I want to stop for a minute and go back to the ramp, the wheelchair ramp. So going back to this wheelchair ramp, I want to talk about the ramps in terms of rate of change. So really, when we talk about rate of change, we're talking about how one part of it changes relative to the other, right? So if I'm talking about a gentle slope, right, then I look at my vertical change not changing very much relative to my horizontal change, right? Whereas in a very steep sloping ramp, then my rate of change is a lot greater, right? So the rate of change of my vertical distance compared to my horizontal distances is a whole lot greater. So a different way to think about slope is in terms of rate of change. So in other words, how fast is one quantity changing compared to the other? And a good example of this is when we're talking about an object moving, an object in motion. We can look at its distance in relation to its time of movement. So for example, if I look at the object that's being represented by this red line here, I can see that its slope is definitely not as steep as the object being represented by this green line here. And one way to look at this would be to examine how far each of them moves in the same amount of time. So for instance, if I'm looking at how far each of these lines have moved in 1 hour, well, the object moving as represented by the red line has only really moved 10 kilometers, whereas the object being represented by the green line has moved in the same amount of time, in the same 1 hour, only it's moved twice as far, 20 kilometers distance. So the steepness of the line itself tells me how quickly the object is moving, in other words, its speed. And of course we know that speed is a measure of the rate of change of motion. So we've described slope as indicating the steepness of a line, and we've shown slope as meaning the rate of change of a line. And then I think you can appreciate that in the real world, there might be places where we need to actually have a calculated slope, right? Where we want to be really precise about that measurement. And so we have a formula that allows us to do that. And it's called the slope formula. So slope can be calculated by taking something we call the rise and dividing it by the run. Let me show you on a graph what that means. So imagine that I have, well, you don't have to imagine it, it's right here. So let's look at a line here that's representing a rate of change or a slope. And the steepness of that line is the same throughout, but we're going to take two specific points on this line and we're going to compare how quickly the line is changing horizontally and vertically. So I know that to get from point A on that line, so let's just call this point A, and to get to point B, and we're going to call this second point, point B on the line, I know that in order to get from point A to point B, I would have had to travel a certain distance horizontally, and that's actually what we call the run. And I'm going to have to compare that to something we call the rise. So in other words, how far I had to rise vertically to get from point A to point B. And you do this every time that you plot a point, right? So if I were plotting a point, I would have to have gone over so far in the x direction and then so far in the y direction. So really, we're just talking about those same movements on the graph, okay? So the run is just the special word we use for our horizontal movement, and the rise is a special word that we use to describe the vertical movement. Okay, so if I'm talking about slope, I calculate that by taking the rise, and that's just my vertical movement, divided by my horizontal movement. So again, one way that I remember, because students forget, sometimes they think, oh, well, is it run over rise or rise over run? So I always think about it in terms of, well, you have to rise out of bed before you can run. So the rise goes on top, right? So again, you have to rise before you can run. So let me show you how you can go about calculating the slope of a line. So here I have a 4-quadrant grid, and so I have to remember that there's some negative values here and some positive values right over here. And so when I'm calculating slope, if it's at all possible, I try to use the area of the graph where there are only positive values, and that just makes the math simpler, and I'm not likely to make mistakes with integers. And the next thing I want to do is I want to locate some points on my line where I know the values exactly, because I don't want to estimate, I want to calculate as accurately as possible. And so I'm going to show you what I mean by that. So right over here, I'm looking at this line, and I can see that this right here, there's a point that's exactly at 4 and 6. 4 and 6. And I'm going to find a second point where I can see my line is exactly on the grid. That looks like right here. So I'm going to plot this. I'm going to just highlight that point right there as well. Now remember that to calculate slope, I need to know my rise and my run, right? So I'm going to just draw this little slope triangle that connects those 2 points, right? And so when I look at this, I can see that my run is 3 squares large. And if my graph is going up by 1 unit, then that works fine to just count squares. But I really need to know what those 3 squares represent. So in this case, you know, I'm going from a 6 right here all the way up to 12. So 6, to 12 is really 6 units, right? So there's 2, 4, 6 units. So my rise is 6. And I'm going to do the same thing on my horizontal axis, right? I'm starting at 4, but my next point goes over to 12. So since each tick mark is representing 2 units, then I'm really going 2, 4, 6, 8. So I'm really going up 8 units, right? And that's my rise. So I've got all the information I need to calculate my slope. Remember that slope, I'm going to use the symbol m just for short form. And that's always equal to my rise over my run. Okay, because I'm going to rise before I run. Okay, and just writing it out a few times will help you to remember not to reverse these, because if you reverse it, then you don't have the properly calculated slope. So my rise here is 6, and my run is 8. And I know that 6 divided by 8 does not give me a whole number, so I'm actually going to leave this in fraction form, and I'm even going to do one better. I see that this is not a fraction written in lowest terms. And so wherever I see this happening, I want to reduce my fraction into lowest terms. So then I have the most efficiently written slope. So I'm looking for, to reduce this fraction to lowest terms, I'm looking to see what the lowest value is that both the top, the numerator, and the denominator, the bottom, can be divided by. And I can see that both of those can be divided by 2. So I'm going to divide my numerator and my denominator by 2. And when I do that, I have a nicely reduced value for my slope. So that gives me 3/4. So my slope, the slope of this line, my slope is 3/4. And I'm done. So here's a friendly reminder to reduce your fractions to lowest terms. All right, so now I think you're ready to take a look at an example. I'd like you to pause the video and give this a go on your own, grabbing a whiteboard and a marker and trying out the question for yourself. All right, so I'm going to take this up. Now, again, it doesn't really matter which 2 points you pick on the line. It's just it makes it a lot easier for you if you pick exact values. So for instance, I see here's a point where that would be a good point to select. Over here would be another good one. Over here would be a good one. The points you pick are closer together, you're less likely to have to reduce a fraction. So I'm actually going to pick this point right here at 1 and 0.5. Ooh, no. Maybe not, because that is going to give me a fraction as well. So I'm going to pick right here 2 and 4. And I'm going to go all the way over. And I'm going to go all the way up. And so again, I don't want to count squares. I want to actually see what each tick mark on my graph is representing in order to figure out my rise and my run. So right here, I'm starting at 2, and this is going to 2.53, and then 3.54. So really, I'm going the distance between 2 and 4, and so that means that my run is 2. When I look at my rise, I'm going from a value of 1 up to 2, so that means that my rise is actually 1. So calculating slope, my slope with the symbol m is always my rise over my run. And so now all I have to do is I have to plug in this these values. My rise is 1 and my run is 2. And so I'm actually good. I have a rise over run. My slope is a half, and I'm going to leave that as a fraction.